Okay. Hello everyone. Good morning. Uh, am I audible to all of you? Darshana, am I audible?
Yes, sir.
Okay. So yeah. So yesterday I have discussed about the step input and the ramp input for step ramp and impulse input for first order system. And again I have developed some mathematical model for uh, mercury thermometer as well as liquid level tank, right? And a capacitive process, purely capacitive process. So here I have derived a purely capacitive process that Hs by Fi bar S that is equals to 1 upon S, where Hs is your deviation variable, I mean height in terms of deviation variable, and F bar S is inlet flow rate in terms of deviation variable, right? So again, once we get this particular formula that that one is Hs upon F bar S, so that is 1 upon As. So here A is your area of tank, fine. So this is our input, this is our output. So let's say let your F bar S that is equals to a magnitude of M by S. This is a step input of this one is a step input of magnitude M. So I can write that Hs is equals to m divided by s into 1 upon as. So can I write m by a and into 1 upon s square. So if I take Laplace inverse of Hs, that is our height, so that is equals to m by a, that will be common, and Laplace inverse of 1 upon s square. Any doubt? So this will give you ht, right? And that is equals to what? M by a, and 1 upon s square is t, right? So now you can write this one is your ht minus hs, that is equals to m by a into t. So once we give a step input to the purely capacity process, you will see this particular formula. Sorry, this particular formula. So here I can write your small ht, your small ht is height of the tank at any time, and hs is equals to steady state height at initial time, right? So you will see this kind of formula. So when we have given a step input, then you can see this particular thing. So now second, for ramp input. So what is our ramp input? So the ramp input will be your f bar s, that is equals to what? M divided by s square. Fine. So we are very much interested in knowing the value of hs, that is equals to your f bar s into 1 upon as. So now you will get hs, that is equals to m divided by s square multiplied with 1 upon as. I am doing the same thing for the purely capacity process, right? So you can write hs is equals to m divided by a 1 upon s cube. Now I'll take Laplace inverse of Hs to understand the dynamics of the system. Again, I'll have to take Laplace inverse of m upon a and 1 upon s cube. Since m upon a is constant, so it will come outside of the Laplace inverse. So finally, you will see that this value give you capital Ht, that is equals to m upon a, and you will get Laplace inverse of 1 upon s cube. And in the previous lecture, I have discussed you Laplace of t to the power n is equals to factorial n upon n plus 1, s to the power n plus 1. So here, s to the power 3 is there. So can I write here s to the power 2 plus 1? So if you'll see Laplace of t square, so you will see factorial 2 upon s to the power 2, sorry, 3. So here I have to multiply and divide by 2 over here. So finally, I'll see the value of st is equals to m upon a multiplied with 2 upon 2 into Laplace inverse of 1 upon s cube, right? And this particular things will become what? T square. So finally you will see m divided by 2a t square. So the height of tank at a particular time, sorry, minus a steady state height, that is equals to m divided by 2a and t square. So at any particular time, if a steady state height initially is given, then you can calculate the height of a tank at any particular time, since it is varying with respect to t square, right? So the plot will look like this one. So let's say this one is a steady state height hs, and if this one is ht, so definitely it will go like that, right? So this will be the plot of this one. Fine. I hope these things is clear to all of you now. So with that, I will move forward towards the second order system, right? This was the first order system where the transfer function was derived from the first order differential equation, and it's a beautiful, concept for process dynamics and control, because most of the industry utilizes first order system, and later on I'll tell you why first order system is very convenient to use in industry, right, compared to the second order system. Okay, so let's start with the second order system. Again, this one is a bit complicated, but yes, it's very important. So the second order system will be derived by the second order differential equation. So that differential equation will be of this type: d tau square d2 yt by d2 square plus 2 zeta tau dyt by dt plus yt is equals to kp into xt, right? Where y is your output, your x is input, tau is time constant of the process, your kp is gain of the system, and your zeta is called as the damping coefficient, right? So I hope these things is clear to all of you. I have written all the individual, meaning of all these particular parameters that involves in this particular differential equation. So when we talk this differential equation, so again, I I mean this one I can assume equation first, right? And if I want to write at steady state, right? So what will happen? Tau square d2 ys divided by dt square plus 2 zeta tau dys divided by dt plus ys, that is equals to kp xs. This one is your equation second. So if I'll subtract equation first minus second, so can I write that tau square d2 yt minus ys divided by dt square plus again 2 zeta tau d yt minus ys divided by dt plus yt minus ys, fine, that is equals to kp. This one is xt minus xs. So again I told you that a small yt minus ys, that will be in the form of deviation variable. I will be writing capital yt, and again xt minus xs, that will be written in the form of again deviation variable. So this one is your in terms of deviation variable. So, but if your ys is 0 and xs will be 0, then your small yt will become capital Yt, and your small xt will become capital X. This is the essence of this particular thing that you need to understand, because if there is a steady state value, then you have to use that steady state value, right? It's very convenient to use to solve some correctly, right? So now if I am I have I mean subtracted equation first and second, and I will write this differential equation in terms of deviation variable. So finally you will see that the value that tau square d2 capital Yt divided by dt square plus 2 zeta tau d capital Yt divided by dt plus capital Yt, that is equals to kp capital xt, right? Now, if I'll tell, let's say this one is equation third. So I'll taking Laplace of equation third. So can I write Laplace of tau squared d2 capital Yt divided by dt plus 2 zeta tau Laplace of, now I can write dyt, this one is capital, divided by dt plus Laplace of yt, that is equals to kp, I'll take common, and Laplace of xt. So now you must be knowing that since at a steady state, I mean at initial time y0, that is equals to y dash 0, that is equals to y double dash 0. And I told you yesterday how we are getting this particular thing y0, y dash 0 and y double dash 0, right? So now for this particular differential equation, I can write that tau square. Can I write that s square y s minus sy0 minus y dash 0. Now you people are very much comfortable in writing this differential equation into the S domain. So I will write 2 zeta tau. I'll write sys minus y0 plus I can write that ys that is equals to kpxs. So finally, after taking the Laplace, I have converted that second order differential equation into the S domain. And now I'll substitute this boundary condition that y0 is 0, y dash 0 is 0. Here it will be 0. So I can write that tau square s square ys minus 2 zeta tau s ys plus, sorry, it will be plus ys that is equals to kp xs. So if I'll take common ys from all side in the left hand side, so I can write tau square s square plus 2 zeta tau s plus 1 that is equals to kp xs, right? So finally, we have reached a conclusion that ys divided by xs that is equals to kp divided by tau square s square plus 2 zeta tau s plus 1, right? So now you can see yesterday I have told you this is a second order differential equation, sorry, second order transfer function. And since this one is your output, this one is your input. So I can write that output by input is transfer function gs that is ys divided by xs that is equals to a small ys. I mean, right now, let it live. So we got a formula that is kp upon tau square s square plus 2 zeta tau s plus 1. So this is the transfer function or second order process in S domain, right? So once we get this particular thing, so what happens? This zeta, I told you that is called as the damping coefficient. It takes care, it take care of oscillatory behavior of the process and what oscillatory behavior of your yt. Let's see how this particular thing will look like. So when we draw the plot of this particular function, so it look like this one, right? It will look like this if you do draw this particular function in MATLAB or Python, whatever the thing is there. I'll tell you later on. So this plot look like this. So it will come like this one. There will be some kind of oscillation over here. Again, for different zeta, if you want to draw, so it can go like that. This can go like that. And again, if you want to draw, it can go like that anytime. So now the thing is that I'm drawing the YT of this particular plot. I'll tell you why I'm drawing. So when we go from this to this, so your zeta will be decreasing. Means here let's say zeta 1, here let's say zeta 2, and here let's say zeta 3. So your zeta 3 will be less than zeta 2 will be less than zeta 1. Means if oscillation in the system is more, then zeta will be very less. So zeta is inversely proportional to oscillation. Just try to understand these things only. I'll tell you this. I'll discuss you later on this particular thing. So zeta will tell you that which system is having more oscillation, which system is having less oscillation. So if in your output, if you want to remove oscillation, then you what you need to do, you have to increase the zeta. So you can capture the oscillation. Or if a system requires more oscillatory behavior, then you can decrease the value of the damping coefficient if this is a second order process. And with that you can increase the value of oscillation of the process. That is what the essence of this particular thing is, right? So with this particular thing, zeta has been, zeta can be zeta may be greater than 0, zeta may be 0, zeta can be less than 1, right? And one more thing is zeta may be equals to 1. So there are four values of zeta has been categorized in with these four parts, right? Since zeta is a parameter of system, zeta is a parameter of the system. Zeta is a parameter of the system. So, I mean, zeta has been categorized in four particular domain, that is one greater than 1, less than 1, equals to 1 and 0. So, when zeta is greater than 1, then process is called as the overdamped system. When zeta is equals to 1, then process is called as the critically damped system. Fine. When zeta is less than 1, then this one is called as the underdamped system. And when zeta is equals to 0, then it will be called as the undamped system. So, on the basis of the value of zeta, the process has been categorized in four parts, that is overdamped system, critically damped system, underdamped system, and undamped system. And zeta can never be less than 0. Zeta can never be less than 0, right? It's very important thing. So, based on this particular zeta, we can plot this particular second order process, and we can understand whether the zeta is greater than 0, less than 0, right? So I have told you that the transfer function of the second order process, that is ys divided by capital X in terms of deviation variable, that is kp upon tau square s square plus 2 zeta tau s plus 1. So now what I will do is, let's say I'll check the roots of denominator of transfer function. And what is this? That tau square s square plus 2 zeta tau s plus 1, that is equals to 0. This is a quadratic equation. Then I can calculate the roots of this quadratic equation. So how can I calculate the roots of quadratic equation? So first I'll calculate the determinant, discriminant. So what is equals to b square minus 4ac. So this one is your b, right? This one is your a and this one is your c. So I can write 2 zeta tau whole square minus 4 tau square. Is it clear? So that is equals to how much? 4 zeta square tau square minus 4 tau square. So you can take common 4 tau square. So that is zeta square minus, right? So once you calculated determinant, so you can calculate the value of s. That is equals to s is equals to minus b plus minus root d divided by 2a. So minus b, so minus 2 zeta tau plus minus root over 4 tau square zeta square minus 1 divided by 2, and a is equals to tau square. Fine. So minus 2 zeta tau plus minus, from here you can take 4 tau square common, so it will be 2 tau, and it will be root under zeta square minus 1 divided by 2 tau square. Is it clear? So finally you can cancel out 2 tau 2 tau. So you can see that is minus zeta plus minus root over zeta square minus 1 divided by 2 tau. So you will get S1 that is equals to minus zeta plus root over zeta square minus 1 divided by 2 tau, and the value of second root S2 is equals to minus zeta minus root over zeta square minus 1 divided by 2 tau. Is it clear? Sorry, 2 tau will get cancelled out. Sorry for that. So here only tau will be there, right? So you have got the root of this particular quadratic equation, and this is the called as the poles of called as the poles of second order process. Simply what I am doing here is you just take this denominator, right? Calculate the roots of this denominator. This is quadratic equation, and you will get two roots s1 and s2. And from here, once you calculate these things, you will see. Say, I mean, we call it as the poles of the second order transfer function, right? So yeah, so we have got a root that is our s that is equals to s1 or s2 that is equals to minus zeta plus minus root over zeta square minus 1 divided by tau, right? So I can write here that is minus zeta by tau plus minus root over zeta square minus 1 upon tau, right? So now tell one thing, if here first, if zeta is greater than 1, if zeta is greater than 1, what happens? 1 square, this will be greater than 1, so this will be also a real part. This will be real and this will be real, right? So what will happen? Roots are real, right? And unequal, right? Because you will substitute zeta is greater than 1. So definitely 1 will be plus and 1 will be minus. So roots will be real and unequal. Now, if I will substitute zeta is less than 1. So if I will substitute zeta is less than 1, so this will be a negative plus minus. If I will substitute here zeta is less than 1, what will happen? This what become will becomes imaginary, right? Are you getting it? So your s is equals to minus zeta upon tau plus minus root over zeta square minus 1 divided by tau. So your this part, no, so your root under part will become plus you will substitute zeta is less than 1, fine. So this part will becomes imaginary. So here roots will be imaginary and unequal, right? So next one is third. If I'll substitute zeta is equals to 1, so your s is equals to minus 1 upon tau plus minus root over 1 minus 1 upon tau. So that this will be equals to 0. So roots is equals to minus 1 upon tau. Are you getting? So you will see that same root and two times. So roots will be here real and equal. Roots will be real and equal when zeta is equals to 1. When I'll talk fourth one, if zeta is equals to 0, so your roots is equals to minus zeta upon tau plus minus root over zeta square minus 1 divided by tau. So if I'll substitute zeta is 0, what will happen? This one will be 0, this one will be 0. So your roots will be equals to plus minus root over minus 1 divided by tau. So that is equals to I divided by tau plus minus I divided by tau. So here you see that roots are unequal, and imaginary. So we have seen all these four condition of roots. Are you getting that how this zeta can affect your process? I'll tell you about roots of the importance of the roots for the process. But till now, we have understood about that how this process can be affected by value of zeta, right? So till now, if I want to summarize over here, so we have got what four value of zeta, and for all four value, I have discussed the process that is one, that is two, that is three, and that is four. Fine. Here, if I take zeta is greater than 1, if zeta is less than 1, sorry, zeta is equals to 1, zeta is equals to 0, and zeta is less than 1. Right? Here, system was called as the overdamped roots, real and unequal. When zeta is equals to 1, root were real and it was critically damped. When zeta is equals to 0, what happens? Root were imaginary, and this is called as undamped system. And when zeta is less than 1, what happens? This one is called as the underdamped system. And this was underdamped system, and root was again imaginary and unequal. So we have seen four condition where these two condition gives a real root. Here you see real roots, and here you see imaginary roots. So let's try to understand that thing. Since if I draw this particular diagram in complex plane, so this indicates the real axis. This indicates the imaginary axis. If I say you that roots s is equals to plus minus 3, s is equals to plus minus 3. So s1 will be equals to 3 and s2 is equals to minus 3. So how will we identify this on the plane, on the number system? So here root will be plus 3 and here root will be minus 3, right? So I can define here one root is here and here one root is here. Now this was the real or real and unequal. When I tell critically damped when root is real, let's say I say s is equals to 3 plus minus 4i. So how can I identify these things? Let's say only I tell you s is equals to plus minus 4i. So this will lie on the imaginary axis only, right? I hope this thing is clear. So S1 is equals to 4i and S2 is equals to minus 4i. So 4i will be here and minus 4i will be here. Are you getting it? Now, if I tell you S is equals to 3 plus minus 4i. So let's say I am drawing here. S is equals to 3 plus minus 4i now. So can I write S1 is equals to 3 plus 4i and your S2 is equals to 3 minus 4i. So if this is your complex plane, this one will be your real axis and this one will be your imaginary axis. So first, this particular first part shows this one is your real part and this one is your imaginary part. So your real part is 3, so you will go at 3 and your imaginary part for first root is 4i. So 4i will be here and minus 4i will be here. So your plot, your root will be here only. This point will be of your root. This will show S1, which is 3 plus 4i, and parallelly here, in this point here, in this plane, in the fourth quadrant, you will see your second root will lie, and this is equals to 3 minus 4i. Any doubt? Tell me. So here you will see 1, 2, 3, 4, 5, 6. Here it will be minus 1, minus 2, minus 3. All I think you know these things. Here it is I, here this will be 2i, here this is 3i, here this is minus I, here this is minus 2i, here this is minus 3i. So your y-axis in complex plane shows the imaginary number, and x-axis in the complex plane shows the real number. So this one is your complex plane. So this is the criteria for the roots in this particular system. Is it clear to all of you? Anyone has any doubt?
Sir, how can we show that the system is overdamped or underdamped? Can we show it on graph, like making
Yeah, yeah. I'll give.
overdamped and underdamped? How can I understand?
Yeah, yeah. Let's understand. So till now, I think you understood this particular thing. Zeta is less than 1, zeta is equals to 1, zeta is equals to 0, and zeta is less than 1, and how the roots will look like, right? So let's try to understand one thing. First, I am talking about when zeta is equals to 1. So this was your critically damped, right? So your value of ys divided by xs, that was kp divided by tau square s square, plus if zeta is equals to 1, can I write 2 tau s plus 1 if zeta is 1? So can I write here that is kp divided by tau s plus 1 whole square? Any doubt? So let's say I am giving a step input of magnitude 1 unit step input. So what will happen? Ys is equals to 1 upon s into kp upon tau s plus 1 whole square. So if I want to convert this one into yt, so I'll have to take Laplace inverse. So Laplace inverse of ys, that is equals to yt, that is equals to Laplace inverse of 1 upon s into kp upon tau s plus 1 whole square. Fine. So now, how do we calculate the Laplace inverse of this particular thing? So first I'll break this particular function, S domain function, into the partial fraction, and after that I'll calculate the value of constant, and from there we can get the value of Laplace inverse. So this function is 1 upon s into s plus tau s plus 1 whole square, and this is kp, can be broken in this form: a by s plus b upon tau s plus 1 plus c upon tau s plus 1 whole square. If I write here, so I can write tau s plus 1 whole square plus bs tau s plus 1 plus cs. Fine. And that is equals to kp directly. So I can write that kp is equals to a tau square s square plus 2 tau s plus 1 plus b tau s square plus bs plus cs. So again, I can write that kp is equals to s square term I'll take common, so I can write that tau square a plus b tau, plus if I'll take s common, I can write 2a tau plus this one, 2 tau square plus here it will be only s, sorry, plus your b plus c, and plus constant is a. Right? So you have got the value of a is equals to kp, and your tau square a plus b tau, that is equals to 0. So tau a is equals to kp, so kp tau plus b is equals to 0. So you have got the value of b is equals to minus kp tau. Now, to calculate the value of C, I'll substitute this 2a tau plus b plus c, that is equals to 0. So 2 multiplied with a is kp into tau minus kp tau plus c is equals to 0. So your c is equals to minus kp into tau. So eventually we have got the value of a, b and c. Now I'll substituting the value of a, b, c over here, right? Let's say this one is equation first. So once you substitute the value of a, b, c over there, so you will get the value of yt, that is equals to Laplace inverse of a. So a is kp upon s. I'll write here kp upon s plus Laplace inverse of your value of b was minus kp. So minus kp tau upon tau s plus 1 plus Laplace inverse of value of c, p is also coming minus, right? So minus kp tau upon tau s plus 1 whole square. Is it clear? So Laplace inverse of kp upon s is equals to kp plus Laplace inverse of this one is how much? Tell me, anyone? Now you should tell me directly. Minus kp. If I take here s common, so what will happen? Sorry, tau common. So s plus 1 upon tau, right? So tau and tau will get cancelled out and it will give you e to the power
Minus t
8.
by tau. Minus
What?
minus t by tau.
Minus t by tau, fine. And this one is minus. If I'll take tau square common, so what will happen here? S plus 1 upon tau whole square, right? And kp and minus, so this will be equals to minus kp upon tau. And what will be the value here? Again, you got trapped, no? This is just a simple thing, yeah. Now you tell, until unless you won't tell, I won't move forward. This should be done by you now. What is the Laplace inverse of, Laplace of t? 1 upon s square. And if I multiply Laplace of t into e to the power at, what will be here? 1 upon s plus a whole square. Are you getting it?
Yes, sir.
Similarly, I can tau s plus 1 whole square, so s plus a whole square. If I am taking tau common outside, s plus 1 by tau whole square. Sorry, it will be minus 80. So directly I can write here t into e to the power minus t by tau. That's it. Anyhow, so if I'll take common kp, so can I take 1 minus e to the power minus t by tau minus t upon tau e to the power minus t by tau. If you will take common kp, so 1 minus, if I take common e to the power minus t by tau, so you will get 1 minus t by tau, 1 plus t by tau e to the power minus t by,
Excuse me, sir.
yeah.
Sir, while taking tau common from tau s plus 1 whole square, so tau square will come out. So 1 tau is also remain in denominator. No?
So that's what I am writing here, no? This tau.
Yes, sir.
This tau is here,
Okay, sir.
fine. So finally you got the value of yt, that is equal to your kp 1 minus 1 plus t divided by tau. This is t e to the power minus t by tau. So for critically damped system, you got the value over here, right? That is equals to t by tau e to the power minus t by tau, right? So now the thing is that we have to understand how the plot will look like. If I want to draw this particular, the plot of this particular function of second order step input, so at t is equals to 0, what will happen? Yt is equals to kp 1 minus 1 plus 0, it will be whatever. t minus tau. So this will be 0. So this will be 0. So this whole term will becomes 1. So 1 minus 1, 0. So your yt will be 0. At t is equals to infinity. What will happen? T tending to infinity, this particular term will become 0 and this will becomes infinity. So infinity multiplied with 0, definitely it will be 0. The whole term will become 0 and it will be equals to Kp. So maximum value, maximum output steady state value, that will be equal to Kp. And again, this will go like that. Are you getting it? This will be, I mean, similarly, it will look like the first order system process. Any doubt? So the thing is that you will see this particular graph. So, and this particular system reaches a maximum value for a step input. This is Kp. But if a step input is having magnitude of m, what will be there? So here you have to multiply with only m. That's it. Here a step input, unit step input was there. That's why 1 multiplied with Kp. But if there is a step input of magnitude of m, then 1 will replace by m. That's it. And no difference will be there. Are you getting it? So this was critically damped system. Now second, if your zeta is less than 1, so your ys divided by xs, that is equals to what? Kp upon tau square s square plus 2 zeta tau s plus 1. So zeta is less than 1. It can take any value 0.1, 0.2, 0.3 up to 1, any value. Is it clear? So the thing is that for every particular value, you cannot calculate. I mean, if you these equations, if I want to tell you xs is equals to 1 upon s, and then I tell you ys is equals to, you will write 1 upon s into kp divided by tau square s square plus 2 zeta tau s plus 1. And after that, you will take Laplace inverse of ys, that is equals to yt, that is equals to again Laplace inverse of 1 upon s into kp divided by tau square s square plus 2 zeta tau s plus 1. So now here, what you will see here, this particular Laplace inverse of these things will become very complicated because it will go in the third order, right? It will go to the third order, and this will leads to a complicated, derivation. So without understanding this Laplace over here, so experimentally, it has been given that for under damped system, that is zeta is less than 1, the plot u of this particular function for the step input look like this one. Yt versus t, and if I say this one, so it will go like that, and it will look like that. Clear? So here the you see ultimately the response is getting settled at this particular line, right? So ultimately, since it will reach to the maxima here, again it will come, it will reach here, again it will go here. So ultimately, what happened after huge time, after t is equals to infinity, this response will settle to a particular value, and this value is called as the ultimate value of response, UVR. This point is called as ultimate value of response. Ultimate value of response, this is called. And for this particular curve, zeta will be less than 1. And I have told you, if zeta is decreasing, your oscillation will
Oscillation
increase.
even.
oscillation will increase. So first try to understand only for zeta is less than 1, any particular value of zeta. Fine. So, so this particular system, if zeta is less than 1, is called as the underdamped system. What is damping? So you see, the damping is like that. This frequency of your maximum amplitude is decreasing continuously with time. That is called as the damping. And dampening the behavior of the system, right? It shows the dampening the behavior, right? Means amplitude of the your output is decreasing continuously with respect to time. That's what the damping is, right? So here there are some, to understand this particular behavior of this underdamped system, some parameters has been defined as. So let's say this one is A, let's say this one is B, and let's say this one is C. This is the amplitude of this particular function. This is also amplitude of here. So A, B, and C are the amplitude of this particular system. So for to understand the underdamped behavior of the system, some parameters has been defined, and the first parameter has been defined as the overshoot. What is overshoot? Means how much this value of this particular function increases in good, I mean get maximum from the ultimate value of response. So this has been defined as overshoot, that is equals to the magnitude of A divided by B. This one is your A, this will be given in the problem, this one is your B. So if this is a wave function, so this is the amplitude of this wave and this is the amplitude of this wave. So if we'll divide both of these two, then it will give you the overshoot value. And mathematically, this is this particular thing. And the formula for overshoot has been given as the, graphically you can divide this A and B, you can get the value of overshoot. And mathematically, the formula for overshoot has been given as that exponential minus pi zeta root upon root over 1 minus zeta square. You don't have to understand how this formula is coming, but try to understand this is the formula of overshoot, right? That's it. Where zeta is your damping coefficient, so exponential minus pi zeta upon root over 1 minus zeta square. So once you calculate the overshoot, you can understand how this thing is related to each other, A and B, right? Now, second thing is that second parameters has been defined as the decay ratio. So decay ratio,
Sir, for our set, we will consider only the first and second, sir. So
yeah,
A
yeah,
and B only will consider now.
only first and second, right?
Okay,
Because
sir.
see, one thing is that here, I mean, maximum value of the response is this one, right? Response can go up to this particular maximum value, right? That is called as a maximum value of response, right? You can write here. So we are very much interested in knowing the ratio of these two peaks. That's it. If only these two peaks ratio, and they have defined that decay ratio is A by B. That's it. So what happens? The ratio here you are getting, it will be similar to the ratio here you will be getting. I mean, a bit similar, most probably, right? That's why they have defined only for first two peaks, right? That is the decay ratio of exponential pi zeta upon root over 1 minus zeta square, right? Any doubt? Okay. If you don't have any doubt, so decay ratio has been defined as, I'm telling you, let's say this one is D. So decay ratio is defined as that A divided by B multiplied with C divided by D, the ratio of two consecutive peaks. And that till now, you can understand the whole behavior of the process. So again, I can say the ratio of A by B is this one. And I have told you the ratio here and here will be equals to the ratio here and here. So I can write that is exponential minus pi zeta upon root over 1 minus zeta square multiplied with exponential minus pi zeta upon root over 1 minus zeta square. So can I write directly this one is exponential minus 2 pi zeta upon root over 1 minus zeta square. Or I can write it directly, that is overshoot whole square. Any doubt? So the decay ratio is nothing but this is the ratio of two consecutive successive peaks ratio, right? That's what I am writing over here. Amplitude of two successive peaks ratio. And the decay ratio value will be equals to overshoot square. Any doubt? So till now we have calculated the value of overshoot, we have calculated the value of decay ratio. This is the ultimate value of response, right? This is the ultimate value of response. Now, if I want to calculate the maximum value of response, so can I write that ultimate value of response plus A? This will give you the maximum value of response. So these are some parameters that you need to understand whenever you solve this particular problem. Any doubt? So if I want to calculate maximum value of response, that is ultimate value of response plus A. Any doubt? Now, one very important thing for the observation over here is, I told you here let's say T and here it is YT. So, hmm. So let's say I am plotting a curve over here. One. So I have plotted three curves and all these are of since if I mean if you see the oscillation in the system, then definitely it will be your under damped system, right? And your zeta will be less than one. That's it. So let's say this one is zeta 1, this one is zeta 2, and this one is zeta 3. Now tell the relation that which one will be correct. Zeta 1 is greater than zeta 2 is greater than zeta 3. Zeta 1 is less than zeta 2 is less than zeta 3. Zeta 1 is equals to zeta 2 equals to zeta 3. And for zeta 1 equals to zeta 2 less than zeta 3. Which one will be correct? Anyone?
Second one.
What?
Second one.
So your option 2 will be correct. Fine. Anyone has any doubt? Tell me. I hope this thing is clear to all of. And now calculate if GS is let's say 2 upon S square plus 2S plus 1. So calculate the overshoot and calculate the decay ratio of the system. First. You have only 2 minutes. Calculate fast.
Zero is some.
Overshoot
Zero
is
is
zero.
coming, sir, but second because
What?
How are you getting zero? So, first of all, your transfer function is like that. Can I write here? That is, try to understand in this way. That is tau square s square plus 2 zeta tau s plus 1. 1 here is here, here it is clear. So here tau square s square, here tau square s square. Tau square here is 1. So tau square is 1, so your tau is equals to 1. That's it. So 2 zeta tau value here is 2. 2 zeta tau is here 2. So 2 into 2 will get cancelled out. So your zeta will be equals to 1. Right? Because tau is 1. So you got zeta is equals to 1, tau is equals to 1. Are you getting it? Fine. So your overshoot is equals to exponential minus pi zeta upon root over 1 minus zeta square. That is exponential minus pi divided by 0. That is exponential minus infinity. So that is equals to 0. So your overshoot will be equals to 0. Is it fine? So obviously, if zeta is coming equals to 1, then it is a critically damped system. So that's why your overshoot and decay ratio will be equals to 0, because the plot of critically damped system will look like this one only. So there is no oscillation in critically damped system. So definitely the overshoot and decay ratio will be equals to 0. Fine. So next, solve this. If I tell you GS is equals to 2 upon S square plus 2S plus 4. What will be the overshoot? What will be the decay ratio? What will be the value of zeta?
So zeta is 1 by 2 and overshoot is 0.163 and decay ratio is 0.027.
Okay, so can I write Kp upon tau square s square plus 2 zeta tau s plus 1? Right? So here there is a first try to understand how you can solve to mitigate the maximum mistakes in your problem. So here it should be 1, but here it is 4. So how can I convert this into 1? I'll divide numerator and denominator by 4. So can I get that 2 divided by 4 divided by s square by 4 plus 2s by 4 plus 1. You don't have to do that much thing, but I'm telling you, once you will calculate these things frequently, you will get to do these things. So this is 1 upon 4 s square plus 1 upon 2 s plus 1. So now you have converted this particular form into the standard form. So here this is 1. So here tau is equals to, you will get to 1 by 2, and 2 into zeta into tau. Tau is 1 by 2, that is equals to 1 by 2. So this will get cancelled out. So your zeta is equals to 1 by 2. So you have got the value of zeta, that is 1 by 2. Since zeta is equals to 0.5, this is less than 1. So this will be your under damped system. So for under damped system, we have defined the overshoot that is equals to exponential minus pi multiplied with 1 upon 2 upon root over 1 minus zeta square, so 1 by 4. And we want to calculate decay ratio. So once you have calculated overshoot, you can calculate the square of this overshoot that is equal to decay ratio. Is it clear? So again, these things, I mean, this kind of questions used to be asked frequently in the GATE examination. So I'd suggest you to focus on the calculation of this particular topic. Anyone has any doubt in this? Tell me. Okay, so if you don't have any doubt, then third characteristics of the underdamped system, underdamped system is rise time, and this will be denoted by TR. So what is rise time? The rise time is, you have seen the graph of underdamped system. If I plot this yt versus t, and if this is our ultimate value of response, so this graph look like this one, right? So the time at which this particular response reaches first time to its ultimate value. This is your rise time. This is the time at which it will reach to the first value of ultimate value, right? First time of ultimate value. You can define the time at which the response reaches to ultimate value first time is called as the rise time, right? The formula of rise time has been given directly with the help of experiment and some modeling. You don't have to derive this. This is just a modeling concept. This is given as pi minus phi divided by omega, where phi is equals to tan inverse root 1 minus zeta square divided by zeta. You have to remember it at any cost. That's it. And omega is equals to 1 minus zeta square divided by tau. So this formula you have to remember, right? This is your rise time, that is pi, and this is, some modeling was there. You have to perform some modeling, and from that modeling you can calculate the value of all these parameter, right? But you don't have to do modeling in GATE. You have to remember this thing. That's now the fourth parameter that comes is peak time. So when we talk about peak time, so our second order under damped response, already I'm drawing so many times. So you can see this look like this one, right? So what is peak time? So what is peak? So this one is your peak maximum. So the time at which this reaches to first time or at its maximum value, TP, right? You can write. This is your peak time. So the peak time that is defined as pi tau divided by root over 1 minus zeta. Again, this is a parameters that has been calculated from some modeling. You have to remember these things. That's it. So you don't have to do derivation and all over here. So this is your formula for peak time. So, sometimes what happens, they will give you this kind of plot, right? And they will give you the time corresponding to all these things. So you don't have to remember these things. Most probably they will give you the plot, and you have to check whether this is peak time, whether this is a response time, and all. That's it, rise time, right? So the fifth parameter is time period of oscillation. All these parameters has been defined for second order under damped system because this is oscillatory only. So repeatedly I am drawing this curve now. So you can see this is your ultimate value of response, fine. So you can see it look like this one, right? So since what is time period of oscillation? So here and here, you see this oscillation is getting repeated. So that's why this is called as the time period of oscillation and it is denoted by T. So this repetitions is called as the time period of oscillation. Means the time period of oscillation, how can we define? I mean the time required to repeat the same kind of oscillation, right? That is called as the time period of oscillation. And we know that omega is equals to root over 1 minus zeta square upon tau. Already I have defined. So we know omega is equals to 2 pi divided by t. So I can define this t its time period of oscillation, that is 2 pi upon omega, and this is 2 pi tau divided by root over 1 minus zeta square. So this is your time period of oscillation. So again you have to remember this. Or sometimes what happens, they will give you the plot and here they will give you value, let's say 2 and 3. So what will be your time period of oscillation? Time period of oscillation is, let's say this one is a minute. So 1 minute. Why? Because this is the time that we are trying to calculate. Na? And from the curve, you can calculate this time. This is only 1 minute. That's why your time period of oscillation is 1. And sometimes they will give you this kind of plot and they will ask you what is the value of zeta if tau is equals to 3. You can calculate the value of zeta because time period of oscillation you have calculated from the graph, that is 1, that is equals to 2 pi multiplied with 3 divided by 1 minus zeta square. They can ask the value of zeta, right? So again they will club the graph and your mathematical formula together, and you need to understand how this particular thing occur. Any doubt? Now what happens over here? So you see this is ultimate value of response. So sometimes response is fluctuating over here. So what happens here, you will see this will come under a particular range right here. It will start decreasing. So here this is 5%, here this is minus 5%, let's say. So from this particular time, what happens? The response reaches to 5% or minus 5% of its ultimate value, right? Ultimate value. So this is called as the settling time, right? So I'll define the next parameter, that is 6.1, and I'll tell you the time response to reach the 95% of ultimate value of response that I showed you over here. So let's say here your response is like that. So this will behave and this will go like that. So finally it will reach here at 95% of this ultimate value, right? This is your ultimate value. So this will come in this particular range, plus 5% range, and this will come in minus 5% range, right? So that's why this particular time will be called as the T settling. So T settling has been defined as in two form, that is 3 tau by zeta and that is 4 tau by zeta, right? So here when error is plus minus 5% and when error is 2%, right? What does it mean? Let's say your ultimate value of response is 10. So when this response value, let's say yt, that is equals to 10 multiplied with 0.95. So it will be reach 9.5. So when it will reach 9.5, when this response will reach 9.5, then this particular t value is called as the ultimate value of response. So how can you calculate this ultimate value of response? So you have to calculate t is equals to 3 tau by zeta. When I am talking about 95% criteria, means 5% error. So you will have to apply this formula. But if I tell you about 2% here. That means 98%, right? So your YT is equals to 10 multiplied with 0.98, that is 9.8. So when 2% criteria is of error is there, then you have to use T settling, that is equals to 4 tau by zeta, right? They will be giving you in the formula in the question which criteria you have to use. Any doubt? I hope there
Sir,
is no
how you
doubt.
have multiplied 10?
What?
Uh, how you have multiplied 10 into, sir, for 95, 10 into 0.95. Y of t is coming 10 into 0.95.
10 into 0.95.
95, sir, how you have put this value?
Since I
10
am
into
talking about,
90.
na, I mean, when it reaches to 95% of its ultimate value, what does it mean that is 95% of its ultimate value? Means here you see there is a fluctuation. Sometimes it will come 10, sometimes it will come 9.5, sometimes it will go 11.5. Again 9.5, 11.5. So these fluctuations will be there. Right? So it will take long times to surpass this fluctuation, right? So it's better to understand now. If I'll get to know the settling time, we can understand, okay, my response is about to come closer to the ultimate value of response, right? That's why if I am getting 95% of its ultimate value, then I'll tell that time is a settling time. But sometimes it is 95% criteria that is filled by this particular formula, and 98% criteria that is filled by this particular formula when the error is 2%. Here error is 5%. That's why 95% I am writing, right? So this is the criteria that should be fulfilled for this, for getting of particular this response, right? Are you getting?
Yes, sir. And so value of 10, 10
Value
y
of,
have used here. So 10.
I just
So
assume
what?
this value. I mean, this will be given in the problem. Ultimate value of response that will be given in the problem. I mean, this is experimental thing. We cannot calculate, right? I mean, how much time it takes to go from Bangalore to, let's say, Delhi. So it should be measured, right? You cannot directly say. So someone has to measure how much time it is taking. Then we can tell, okay, maximum distance or maximum time taken by Bangalore to Delhi is this much. So that is the ultimate value, right? And from there, if I am reaching into 95% of that, let's say it takes 30 hours to reach from Bangalore to Delhi, Bangalore to Delhi. So if I take 95%, let's say 27.5 hours or 33.5 hours. So in between, I'll be reaching there. So I can roughly estimate this particular thing. So at what time I am reaching, I can reach, right? So that is the settling time over there. So for the response, this is the settling time, and how much it reaches to 95% or 98% of its ultimate value, right? Any
So
doubt?
what?
Right? So now this was some parametric form of some. We are about to, know the some parameters relating to the second order system, right? So the more important
Sir,
thing is that,
so what about overdamped systems, or you have just discussed underdamped and critically damped?
yeah, yeah.
Sir, when so zeta is
So
greater than 1, sir, how graph will vary?
so when zeta will be greater than one, so I told you, let's try to understand how this will look like. So try to understand. I'll plot only one plot of all this. So this one is your yt, this one is your t. When we talk about under damped, so definitely oscillation will be there, right? So
Yes.
here zeta will be less than 1. And when we go from this to this, zeta decreases. So if I want to go from this to this, zeta should increase. Fine. So if I tell you, I have this particular curve over here, and I have this particular curve over here. So if I am going from this side to this side, zeta is increasing. Fine. So definitely if this one is zeta is less than 0, then this will be under damped system. The plot of overdamped and critically damped look like same, but here zeta is less compared to this point. So this will be called as critically damped, and this will be called as the overdamped. Fine. Since zeta is increasing this way, so more zeta, more value of response. So here zeta is less than 1, zeta is equals to 1, zeta is greater than 1. That's why this is overdamped, this is critically damped, and this is your underdamped system. Is it clear?
Yes. Yeah.
And all these system are of second order system. That's why only all these things overdamped, I mean zeta is defined for the second order system. Fine. Now, since when second order system is introduced, so it will slow the process. I mean, wait 1 second. Your process later on I'll discuss. Let's try to understand that combination of second order process. Then I'll so till now you have understood this critically damped, the plot of critically damped under that and overdamped system, right? Any doubt? So first I'll be discussing about the applications part, and after that we'll draw all these things. So your application part of so the application is called as divided in two parts. So first is interacting system, and second is non-interacting systems. Ideally, I should write first non-interacting and then interacting. But okay, no issue, I'll write. But I'll be discussing first about non-interacting, because then after I'll move towards the interacting. So this one is non. So what is, I mean, I will be discussing about the only liquid level tank. Yesterday I have told you. Fine. So this is non-interacting. What does it mean non-interacting? So if there is inlet flow rate over here, so this will be filled by water, and here there will be outflow rate for this particular tank. This there will be a valve. This provides a resistance value R1, right? And once I'll open the valve, this flow rate will go into the second tank, right? And the second tank will start filling, right? And here there will be a valve to analyze the outlet flow of this particular tank, and the resistance incurred by valve is R2. Is it fine? So the basic essence of this particular process is that, so there is a tank in which there will be some inlet flow rate here initially Fi, and I am assuming the liquid density is rho. The area of this cross section of this particular tank is A1, fine, and the height of this particular tank initially is H1, fine, and having a resistance in this particular valve is R1, right? After that, what happens? The outlet flow rate over here by tank first is, I will be assuming F1. Again, this particular outlet of first tank will be the work as the inlet of the first second tank, and I'll be assuming height of the second tank is S2. Means what is the height of the water level in this particular tank, and the resistance incurred by this particular valve by after the second tank is R2, and the final output flow rate outlet flow rate of this particular tank is F2, right? So I hope this diagram is clear to all of you. What I am trying to understand. So here I'm the density of fluid is not going to change. The density will be always same. Here the area of cross section may be same, may be different, right? Here if it is, I'm just using the different because we can at the end we can use the same area kind of thing. That depends upon the your value, right? So here area is A1 and A2. So this is the basic, you know, diagram of this particular thing. So if I want to calculate the time constant that yesterday I have discussed, tau 1, that is equals to, can I calculate that is A1 into R1, and here the time constant for this particular tank tau 2, that is equals to A2 R2. Fine. So this system can be broken in two parts. First, this one is a single phase tank, and second, this one is also a single tank, right? Any doubt? I can break this. But directly I can write the relation between inlet flow rate and height of this particular tank, inlet flow rate and height of this particular tank. But we are very much interested in understanding the value of height of this particular tank with, if I'll change the inlet flow rate over here, and flow rate of this particular tank out of this tank with respect to inlet flow rate here, right? So our aim is aim is to understand what is the value of H2S divided by FIS, and what is the value of F2S divided by FIS. So this is our aim, and that we are very much interested in understanding these things, right? So if I talk about transfer function of first tank that I have discussed yesterday, right? So here this one is height H1 H. So can I write H1 in terms of deviation variable H1S, that is equals to H1T minus H1S. Any doubt? You must be knowing these things now. So I'll be using all these things over here. So first I'll be using H1S, that is equals to H1T minus H1S, or FIS bar, that is equal. I will be directly using this in terms of deviation variable. Don't bother about that, right? So you know the value of all these deviation variable, how I can write. So first I can write that yesterday I discussed these things, H1S divided by FIS, that was equals to R1 upon tau 1 S plus 1, right? Yesterday I have discussed these things. If this is your first tank, so I have derived the relation of deviation variable of this particular tank with respect to F1. Yesterday I discussed this, right? Now I will be assuming this one is first. Now transfer function for second tank, similarly, since this is a non-interacting system, so directly I can write. Why this is non-interacting system? The meaning of that is the height in this particular tank H2 will not depends upon the height in this particular tank. Are you getting it? This depends upon this inlet flow rate over here, right? If inlet flow rate will increase, then height will increase. If inlet flow rate will decrease, then height will decrease. If H2 is not going to depend upon, since H2 is not the function of H1, then it is called as the non-interacting system, right? Is it clear? Since or the meaning is that the output of the second tank, that is our H2, is not the function of the output of our first tank, that is your input, then it is called as a non-interacting system. You can say it in this way. Fine. So the transfer function for this particular H2S, and I can write divided by F1S. Why? Because here input is your F1. Here input was Fi. So yesterday I have derived these things. So that is equals to, I can write R2 upon tau 2s plus 1. That is equals to equation second directly. And our objective is to, let's say I want to calculate H2s and F2s. So I want to know the H2s by FIS. So here H2s is here and FIS is here. Now tell me, how can I calculate the value of H2s and FIS from here? And one more thing that is very important. So yeah, yesterday I have discussed that F1s will be what? H1 by R1, and F2s will be equals to H2 by this R2. Already I have discussed these things. So these things also I can write here. So F1s, that is equals to H1s divided by R1, and you can write your F2s, that is equals to H2s divided by R2. So now tell me, how can I get this value H2s by FIS?
Second by first. Divide.
If I'll divide second by first, but FIS again it will go up. So let's try to multiply it first and second. So what I will get, that H1s divided by FIS multiplied with H2s divided by F1s. Can I write R1 divided by tau 1s plus 1 into R2 divided by tau 2s plus 1? Now H2s is here, FIS is here. So this is our ultimate goal, to calculate. We are very much interested in calculating these things. So I will be writing these things together, H2s divided by FIS. Now remaining left is H1s by F1s. So H1s by F1s will be equals to what? R1? Tell me. This is your F1s. So can I write this one is your R1, that is equals to R1 divided by tau 1s plus 1 into R2 divided by tau 2s plus. So this R1 and R1 will get cancelled out. So finally you will get the value H2s divided by F1s, that is equal to R2 divided by tau 2s plus 1. Sorry, FIS, sorry. So the meaning is that if you want to understand that H2s here by FIS, directly you are do the value of R2 divided by multiplication or transfer function of both the function that we are getting here. Okay, here that will be tau 1s also. Fine. Any doubt? Yesterday, this kind of similar thing I have tried. Fine. So our first goal we have completed. Now, how can I calculate the value of F2s by FIS? Tell me. So let's say I want to calculate the value. F2s is what? Outlet flow rate from the second tank. Is it clear? And what is FIS? Inlet flow rate of first tank. And in terms of deviation variable, I am writing. So can I write that F2S divided by F1S and multiplied by F1S divided by FIS? Any doubt? And let's tell me what is your F1S? That is H1 by R1. What is your F2S? That is your H2 by R2. So F1S divided by, and first thing. Second thing is that what is your F2S divided by F1S? That is 1 upon tau 2S plus 1. And what is your F1S divided by FIS? That is your tau 1S plus 1. Is it clear? So here directly I can write F2S divided by F1S is equal to 1 upon tau 2S plus 1. That is 1 upon tau 2S plus 1 multiplied with 1 upon tau 1S plus 1. The essence is here. So if I want to calculate outlet flow rate with respect to inlet flow rate in the first tank, I'll be directly multiplying the transfer function of both the tank, right? And if I want to calculate height of the second tank with respect to height of the first tank, I'll be writing R2 resistance by second tank divided by multiplication of both the tanks transfer function. That's it. When the tank is non-interacting in nature. Is it clear? Tell me. Any doubt? So if you don't have any doubt, just solve one problem. This is the last thing that of today. This one is a tank. Again, I'm telling you this is very important concept. I mean, gate will very much simplified you put the question, but you need to understand, right? So and try to solve very fast. This one is R1. The area of cross section is, let's say, 1 meter square, and the inlet flow rate is, let's say, 10 meter cube per second, and R1 is equals to, let's say, 0.5, R2 is equals to 1, A2 is equals to 2, fine, and yeah, here your height is h1, here your height is h2, right? And yeah, so calculate the value of height of the tank h2 is equals to what? Tau 1 is equals to what? Tau 2 is equals to what? And this one is your f2, this one is your f1. So what is the value of f2 divided by fi, and what is the value of f1 divided by fi, and what is the value of f2 divided by f1? Calculate for it.
In terms of S values come like height of S2.
Yeah, in terms of S only, that's it. After that, we'll give some step input and all. Only this will give you the transfer function, right? I think you cannot calculate the value of height h2 directly right now. So better you calculate the value h2 divided by fi. Subjected that h1s, that is equals to h2s. At a steady state, let's say it is 0 right now. That's it. In terms of only, you can calculate value this one, what I am writing over here, in terms of S domain only, right? That's it. Anyone has calculated?
Yes, sir.
So the thing is that it's very simple. First, basic things what you need to calculate, that is tau 1, tau 2 and all. So first I'll calculate tau 1 is equals to A1 R1. How much? A1 R1 is half. What is tau 2? That is equals to A2 R2. That is equals to what? 2. So next is F2 by FIS. So what is this one? Here that is F2 by Fi. So what I told you, that is multiplication of only transfer function. That is 1 upon tau 1 s plus 1, tau 2 s plus 1. So that is equals to 1 upon half s plus 1, 2s plus 1. So this one is done. What is F1s by FIS? F1s by FIS. What is this? So the value of F1 by Fi. So that is equals to 1 upon tau 1 s plus 1. That's it. What is F2 by F1s? F2 by F1. That is equals to again that 1 upon transfer function of this one. Tau 2 s plus 1. So you solve this one. You solve this one. Now H2 by Fi. H2 by Fi. So recent just I have discussed the value of H2 by Fi, that is equals to R2 divided by tau 1 s plus 1 and tau 2 s plus 1. So R2 is your 2 divided by tau 1 s half s plus 1 and 2s plus 1, right? So this is the case. So again, if I'll change Fi, if let's say Fi is 2 by s, if I am giving a step input of a magnitude 2, how height will be changing? I'll be discussing these things tomorrow, right? I mean, in the next lecture, right? So till now, I hope you would have got the essence of how we can understand this particular dynamics of this particular system, how we can calculate the transfer function. Once you calculate the transfer function, after that, the thing is very easy for you to change any kind of input, either step input, ramp input, sinusoidal input, whatever the input you want to provide for the system, you can get this kind of output for as a dynamics of the system. Anyone has any doubt, tell me. You are left with 5 minutes. You ask the doubt only now in 5 minutes. If any doubt you have, because I won't be teaching the next new concept. And next thing is that you go and start solving problem from previous year question. Okay, sorry, I forgot to send you the previous year question paper. Today I'll send you the previous year question. And now I hope in process analysis and control, I have taught you. I mean, most of the topic I taught you. Now I will be discussing about the controller and after some frequency response kind of thing. So definitely it will take 6 to 10 hours. In the next week, I'll be trying to complete this particular topic again, process dynamics and control. And after that, I'll be starting fluid mechanics and mechanical operation parallelly. So within September or first week of October, I'll be completing all mechanical operation, fluid mechanics and process dynamics and control. And after that, the only two topics that will be left is heat transfer and mass transfer. So again, I'll start heat transfer, and after that, at the end, I'll be teaching the mass transfer. So mass transfer can go to the first week of January. That does not make, don't bother about that. I'll try to complete these two topics in November and December mostly, right? So do you have any doubt, or I should end the meeting now? What is the open loop and the closed loop system in non-interacting? Yeah, open loop, closed loop, all these transfer function. When I will be discussing about that, the loops, na? I'll be telling you, I will be discussing about how to solve this loop kind of problem. All these things basic from, I will go from basic student. All these things I'll be teaching in the next class. Don't bother about this. Right now I am just teaching about how to calculate the transfer function of any physical process. If any physical system, if any physical process is happening, how we can get the transfer function, how can we model that transfer function, and how can once you get the transfer function, then you can then you can perturb any particular system with respect to your any input, a step input, ramp input, sinusoidal input, or impulse input, and then you can understand the dynamics of the system, right? Once you get the idea of transfer function, then we can move towards the loop. all these kind of loop, how actually industry works with respect to how all these instruments are connected in a loop and how these will work. So again, I'll discuss about the controller and all in that particular system, right? Any else? Anyone has any another doubt? Okay, so if you don't have any doubt, then we should end the meeting now, right? So thank you all for attending the class.
This
Thank you, sir.
Yeah.